Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today what I want to do, I want to show you how to use a scope that can do Bode plots, how easy it is to do the impedance curve of, say, an inductor in this case. Resistor, capacitor. You might have some parts around you don't know the value is, or maybe they have iron cores, ferrite cores, and they can change our frequency. You just want to check it out and see what the impedance is or frequency. Maybe you're going to modify an inductor like this, maybe take some turns off, and you want to check the impedance. And so we know that, no part's perfect. They have parasitics, we call them. An inductor will also have some resistance, for instance. A capacitor will have some resistance. A resistor might have some inductance. So we like to get non-inductive resistors for our load banks and that, right? For audio type stuff at least. And even for power supplies. We want to know what we're testing with. So in this case, an air core, even though it has wood dowel on here, there's still some air in the middle. But the wood dowel is not conductive. It's not going to help, induce a magnetic field, and therefore it won't reduce the magnetic field either. So an air core is a little bit more ideal as far as a choke goes, as far as an inductor goes. It does have some resistance, so we're going to see how that works out, okay? And you know what? Let's do some quick math here just to kind of show you this stuff before we get into that. Okay, the equation for an inductor is X of L is equal to 2 pi FL. So as frequency goes up, say it doubles, then X of L will double because they're proportional, right? And so it'll look something like this, X of L or frequency. And let's just say we're going to pick out 1 ohm. And the reason why, if we come over here 1 ohm and look at the graph, we come down, we can calculate what F is. Because we can just cross multiply. And we can, it'd be F would be equal to the X of L, the 1 ohm, divided by 2 pi L. So we could cross multiply and solve F. Okay? In this case, we know what L is. It's a 1 millihenry inductor. This speaker choke, this crossover choke. So we're going to, so I'm going to show you something here. The scope, it'll do things in decibels, and the reason why is because decibels kind of condense things, they kind of collapse things together. And the good thing about that is, like, let's say if you're New York City, some big city, really tall buildings, and if you're looking down at the people down below, they look like little gnats. You can't compare how tall people are. You could be looking down at a 7-foot person compared to a 4-foot person, you wouldn't be able to tell the difference, right? But with logarithmic stuff, you'll get to see small things and big things, because it kind of condenses the big things more than the little things, and so you can kind of get some definition there. So log is commonly used. Well, the log, 20 times the log of 1 ohm is 0 dB. So that's a good starting point, all right? So if you graph something, you graph it, come over and see the frequency. You can come up here and calculate what the inductance would be just by, like we talked about. In this case, what we're going to do is we're going to change that formula to this formula, this guy. So we're going to say X of L divided by 2 pi L is equal to F, okay? So this stuff right here, we know that we're going to look for the case where impedance is 1 ohm. X of L will be 1 ohm. We know it's a 1 millihenry inductor. So we solve for F. That's going to happen at 159 hertz. Okay? And resistance turns out to measure at 0.37. It actually states it on the coil. And we're going to confirm that over here. So when you come down here and look at the curve, you can draw your line for the X of L. But and if X of L, let's say this is the 1 ohm point where it touches the curve and comes down, if the resistance is 0.37, that'd be right about here, and that'd be a straight line because it doesn't change with frequency. Well, where it hits our curve, so the impedance, the Z, the overall impedance, is going to be this. X of L is going to come down, but it can't drop below the R because that's part of the impedance, so then it's going to, level off. And the way you can kind of draw that is at the corner here, you can come up 3 dBs and drop a dot and then kind of round it off. And it kind of looks, to what you're going to see on the scope. Okay? So let's go ahead and take that measurement. Okay, and by the way, I'm giving this away on Father's Day, just a couple days from now, to Patreon. So, and then we're going to give this guy away on July 4th with some other stuff I'm going to put together. Yeah, I got to do something for my Patreons, right? It's only $1 a month to be a Patreon, but I really appreciate them. I appreciate all you guys watching the video. So, anyway, let's get into this video. Okay, thanks. Alright, so here are the tools we'll use. We'll use this Handtech CC65 in the ×10 position, and we'll zero it out here. We're going to use a scope probe in the ×10 position, and then this is coming from the arbitrary generator from the scope, okay, the GW Instek. And here is the guy we want to measure. And here is a FLIR meter that I just reviewed, the DM92. And we can measure the resistance with this guy. We can't measure inductance with it, but we can use the scope. That's the whole point of this. Because a single measurement of inductance, even if we could do that, might not be as telling as if we can see what it is across the frequency band. So let's go ahead and measure the resistance of this. 0.47 ohms. Okay, 0.47, settled there. Now put the probes both on one so we can measure what the probes are. Okay, about 0.1. So it's about 0.37. Subtract that from the first reading, it's about 0.37. And lo and behold, look at this. Look at that, 0.37. And that's flat leads are equivalent to 16 gauge wire. It's a 1 millihenry coil. But we're gonna check that out. We're gonna verify. Janssen Audio, Denmark. This is a really high quality, really cool coil. Air core, or should we call it wooden core? Well, it's wooden and air, right? It has this nice heat shrinked plastic protector. I got this from Parts Express. Or did I get it from Amazon? I'll have to check. I'll get back to you. Okay, so now let's measure. Okay, so we're done with this guy for now. Just move that aside. Let's put the generator on. We're going to put a frequency right across the coil and make sure we don't touch the leads. Now this current probe, we're going to read the current, and so the current wants to go down. It wants to go down into it like this. Okay, there we go. And then we'll put the voltage probe here, right across the coil. Alright, there we go. That's our setup. So we're reading the voltage across the coil, and we're reading the current that goes into it from the generator. And then we're going to take voltage divided by current to get X of L. Or impedance, let's call it. Because we have resistance plus X of L, so it's really Z, impedance. Alright, so let's check this scope setup, okay? Let's turn off that math. And we have channel 1 and channel 4 set up. 4 is a current probe. I just had it chosen for another test I was doing. So it's right over here on channel 4. Okay, so right here. And what we do is we highlight it. Current probe, it's 10x. That's good. Set there, set for current. Great. And you know what? Let's go ahead and just AC couple it. Well, I want to DC couple just to make sure that I have it. See how it's offset right now? I just want to make sure I have it degaussed. So when there we go. Now it's degaussed. It's in the center of the screen. So, okay. Full bandwidth, all that stuff. We haven't changed anything there. So let's go channel 1 ×10 as well. And this one will AC couple just so we can, the volts per division, we can zero in on the AC voltage. Okay, so then what we do is we go to the application button, okay, and then I hit the app, And then see the FRA, frequency response analyzer. So let's come over there. So we have it selected, and then we just say yes, we want that. Yes, we really want it. And then there it is. Now the way this window looks, okay, I think I'm going to just zoom in on the screen. Okay, so let's start off looking at the reference circuit, okay? And what it shows is the scope and device under test. Generator 1 comes out, goes into the input of the device under test, and then with the other channel you measure output. Now I say the other channel because you can actually assign channel 1, channel 2 as anything you want. Okay? So let's see how that's done. Okay, first I turn off the reference circuit, and then I can go to setup, and right here I can assign channel, the input source to be any channel, and we're going to say the input's current. Okay, and so we'll say channel 4, and then the output can be any channel. We're going to say the output's channel 1. So channel 1 is the voltage, and so it'll be output divided by current. Okay, and then we go to generator setup, 20 hertz we start, and we're going to stop at 1 kilohertz. And amplitude is pretty much maxed out, I think. Oh, there we go. Now we're maxed out. Okay, 2.5 volts, and then low impedance. It's going to be pretty low impedance. So we go back. So that was the setup, and then we can go ahead and run it. Okay, so let's go ahead and do that. So we hit run. Alright, so you'll see these scales changing because they auto scales the signal crosses. This is the gain, the blue. There's the gain. And this is the phase, the red, right here. So the gain started off under -4. There's -9, so say -6. Up here you can see the signals. The green one's the current, the yellow one's the voltage. And it'll change the frequency and auto scale the horizontal band and everything, so that's why you kind of see it moving around. And it keeps the signal, you know, it auto scales the vertical and the horizontal. Okay, and this is 1 kilohertz, and this is 100 hertz here. And we're just getting there. Okay, if you notice, it started off, and there's -6. So it started off right around -6, and then right around here it went inductive. So this is resistive where it's flat, and then inductive is this, and they kind of cross. So the inductance curve, you could have drawn it, you know, if you drew it, you would have drew it right across here, and resistance you would have drew across here. And that's where they kind of collide, right about there. Alright, so what we can do is go to measurements here, and FRA measure. Let's hit that. No, let's hit the scale. See the scale? We want a 0 dB on the scale, make it easier to read. So gain offset's 4. Let's push that, and let's put that at 0. See over here? We want to put that at 0, right in the middle of the screen. There we go. So now we have a 0 dB. So now, and the gain is 5 dBs per division. Okay, so 0, -5, and +5 is up here. So you can see easily that we cross over right about there. And that's right in between 100 hertz, 200 hertz. And then it goes 300 hertz all the way up to 1K. Now the phase, we can also change the scale. There's a scale. Here's an offset. It's at 33. Let's put that somewhere. Well, look at that. We're using up pretty much a whole screen. So let's put that at like 30. Since we're at 15 per division. Okay, we're at 30 and 15 per. So now it's easy. 30, 45, 60, 75, so on. And the phase starts to look inductive, and it goes, it should be approaching 90 degrees. Where it crosses over right here, you would have thought maybe 45, but since it had resistive kind of, you know, started off down here, then we're about 15 degrees right there as it started to go this way. So 15 plus 45 puts it right about 60 degrees where it crosses over at 0. Okay, instead of having to kind of guess, we can go to measure, and then we can turn on cursors, and there's our cursors right there. So let's switch to cursor 1. Let's put those first, right where we think it started. See where the ramp went? I'm going to just put that down right where, okay, right there it starts to level off, right in that frequency range, which that says about 70 hertz is about 37 degrees and about minus 4 dB. Then we go to 2, and we can put that right where it's about 0 dB. That's about as close as I can get, I guess, right there. So about 0.1, and that was 60 degrees. And the delta is right there. So yeah, pretty cool stuff. And that's how we can tell our inductive. That's so where it crosses 0, we can do some math, and we can find out where the inductance is. And if we did it at that frequency, and then at frequency up here, let me see if I change these actually. Let's put that right at about, let's put this right at 10 dB. Okay, that's right about as close as I get, I think. And then let's put this one right where it crossed 0. Okay, so if we take each one of those, we can calculate, you know, what at 10 dB, what the 10 dB happens at 500 hertz, and 0 dB happens at 140. We can use those and calculate and see what the resistance should be, and we can see what the inductance should be. Hey guys, what do you think? Hey, by the way, give the video a thumbs up, okay, if you liked it. It really helps the YouTube algorithm thing. It is really helpful. Thanks, guys. Okay, let's just score some math real quick. Just kind of put the whole thing together. Hopefully you can see all this. So the curve we had was in dBs, you know. So we were looking at impedance in dBs, and we took two plots. One at 0 dB and one at about 10 dB. And 10 dB is about 500 hertz. This is frequency. And at 0 dB we had about 140 hertz. Okay, so we had those 2 points on the curve that we could calculate our inductance. If we take this and take 20 times the log of this, if we log that and do 20 times, then we get these numbers here. So if we want to go backwards and find out what x of L is, then we have to divide both sides by 20, which gives us x of L in decibels over 20 is equal to log of x of L. And then we got to get rid of the log, so we get x of L by itself. So you take the anti-log, which is that 10 to the x power thing. So you get 10 with this in the power is equal to x of L. And that's what this is. So you take this 10 dB, divide by 20 dB, and put it in your calculator, that 10 to the x thing, and you get about 3.16 ohms right here. And then, you know, the 0 dB, we know that's going to come out to 1 ohm. So 0 dB divided by 20 dB, you know, 10 to the x, you get 1 ohm. Okay, now we go back to this equation and we solve for L. So we divide both sides by 2 pi f, so we get L is equal to x of L divided by 2 pi f. And for the 140, it'd be this, and that came out to about 1.13 millihenries, and the 3.16 came out to about 1 millihenry. So, you know, I did a little bit of rounding things. I think these probably both would have came out closer to being equal, right? Because that line's pretty straight. So we can do the math to kind of calculate the impedance on the curve and come out and see what it looked like. And plotting points like that, especially when it's a straight line, you pretty much guess that it's not going to change. But just to prove to yourself, you can take a couple points like this. Since we started off at 0.36 ohms, and then we go to only 1 ohm, maybe that was a little bit too close to take that measurement. Maybe that's why it threw it off a little bit. Still kind of the curve wasn't going quite linear at that point. But alright guys, hey, I hope you liked this. Remember, thumbs up, and we'll see you next time.